In this video, we're going to learn how to write equilibrium expressions, and we'll also learn how to calculate the equilibrium constant. So the equilibrium constant is a constant for a reaction at equilibrium, kind of self-explanatory. It's at a given temperature, so if the temperature changes, the equilibrium constant will change as well. And we calculate the equilibrium constant using the equilibrium concentrations of the products and the reactants. And we also take a look at the coefficients of the balanced chemical equation because they're involved as well. So the equilibrium expression is a ratio of the equilibrium concentrations of the products and the reactants. So imagine we have this chemical reaction here. So the small letters are the coefficients of the reaction, and the large letters are the elements or compounds in the equation. So we calculate the equilibrium expression in the following way. So the equilibrium constant is equal to the concentrations of each of the products to the power of their coefficient multiplied together, divided by the product of the concentration of the reactants to their power of their coefficient. Now there is one thing that we need to keep in mind. We only include gases and aqueous solutions in the equilibrium expression, and that makes sense because they're the only things that would have concentrations. If you have a solid state or a liquid state, it's 100% that thing. Okay, so now we're going to practice. So imagine we had this chemical equation right here. So now we need to write the equilibrium expression. So Kc is going to equal the concentration of NO2 to the power of 2 over the concentration of NO to the power of 2 times O2. That's the equilibrium expression. Okay, now we're going to practice with another one, but remember, you need to look at the states or the consistency of each of them. So this one is water liquid, so we don't include it in the equilibrium expression. So this time it's going to equal, so Kc is going to equal H2, the concentration of H2 squared, times the concentration of O2. And that's it. We don't include water because it's a liquid. So now we're going to talk about what the magnitude of K tells us. So if K is much smaller than 1, so far below 1, the reaction will only proceed slightly. That means that the reactants are going to be favored and the products are not. If Kc equals 1, neither side is favored, so you'd have about equal concentrations of products and reactants. And then finally, if K is much greater than 1, the reaction is said to proceed to completion, so the products are going to be favored and not the reactants. So that value of K can help us determine what type of equilibrium our system is in. So once we know the equilibrium concentrations of our products and reactants, we can calculate the value of K. So in this example, we are saying that a mixture of hydrogen gas and iodine in gas state reacts at 448 degrees Celsius. At equilibrium, the concentration of hydrogen was 0.46 moles per liter, the concentration of iodine was 0.39 moles per liter, and the concentration of hydrogen iodide was 3 moles per liter. We're being asked to calculate the equilibrium constant Kc. So the first thing that we need to do is write the equilibrium expression. So Kc is equal to, remember it's the concentration of the products over the concentration of the reactants to their powers of their coefficient. So it's going to be Hi squared over the product of H2 times I2. And then we will now sub in our values. So that's equal to 3.0 moles per liter squared over the product of the two reactants, so 0.46 moles per liter times 0.39 moles per liter. So that's going to equal 9.00 moles per liter divided by 0.1794 moles per liter squared, both of those. So that's going to equal 50. So our equilibrium constant is 50. If we go back to talking about the magnitude of K, it's bigger than 1, quite a bit bigger than 1. So that tells us that the reaction proceeds towards the product. So the products are favored in this equilibrium expression. So manipulating K. If we reverse a reaction, the Kc, the equilibrium constant, will become the inverse of the forward reaction. And when you think about that, that does make sense because you would rewrite the equilibrium expression and the products and reactants would flip position, so it would be the inverse. So if we had this reaction, and Kc is 794 at 298 Kelvin, the reverse reaction would be inverse. So you would just take 1 and divide it by 794, and you get 1.26 times 10 to the power of negative 3 at 298 Kelvin. Also, if you double the coefficients, the equilibrium constant would be squared. If you have the value of the coefficients, it would be the square root of the original, and so on. So in this case, if we had this, and we took the reverse, or we took the forward reaction, but halved each of the constants, the Kc would be the square root, or to the power of a half. Also, if the reaction occurs as a series of steps, the equilibrium constant would be the product of the equilibrium constants of each of those individual steps. So in this example, we're being asked to find the equilibrium constant for the reverse reaction. So in this case, that would be the inverse of the forward reaction. So it would be 1 over 9.60. So that's going to equal 0.104. So now it's much smaller than the forward reaction, so it's not going to be favored. I would like to note that the examples used in this video were adapted from the Cognity IB Higher Level Biology textbook.